Good morning, ladies and gentlemen. My name is Viljoen, and in this video I will go over the project that my team and I were tasked with doing over the past few weeks. We were tasked with analyzing the house prices of residential homes in the city of Ames, Iowa, and then making predictions on the sales price for these houses, all using regression techniques and models. The data we received was comprised of a training set and a test set. The training set had 79 different variables, each variable specifying a specific feature of the house, thousands of housing records, and also a sales price for each house. The test set, on the other hand, had these same 79 variables, but different housing records, and also excluded a sales price for each housing record. We also received data descriptions for each column, so that we knew specifically what each feature was supposed to represent in each house. After importing this data, we performed a few quick visualizations, and we could see, after visualizing the missing data in each dataset, that there was a significant, non-negligible portion of the data missing. After this, we performed a visualization of the sales price variable, and we could also clearly observe that this data was highly skewed to the right, with a few outliers and a few extreme outliers as well. After that, we performed a visualization for the data records associated with each neighborhood. We could also see that there was a significant disparity in the data representation among the neighborhoods. We therefore concluded that our prediction would be significantly more accurate for houses in the high represented neighborhoods than they would be for houses in the lower represented ones. Then, going into the data preparation phase, we made multiple alterations to the original data so that our predictive models would be better able to use them. First, we decided to tackle the missing values. From the data descriptions provided by Kaggle, we could see that some of these missing values are known as false NaNs. An NaN value in these columns don't mean that the data is missing for that column. Instead, it means that the house is simply lacking that feature. For example, an NaN value in the pool QC column simply means the house doesn't have a pool. Therefore, any connected numerical columns that are supposed to detail these missing features also needed to be changed. In order to correct this, we filled all the NaN values in these categorical columns with none, while replacing any NaN values in the appropriate numerical columns with 0. After this, and with a few more visualizations of any remaining missing data, we could see that there was still some missing data. These were true NaNs, and to fight these, we also replaced the NaNs in these categorical columns with the mode for their columns, and the numerical missing values with a median for their respective neighborhoods. After this, we did a few more things, but they were pretty insignificant overall. But namely, there were things such as dropping a few columns that provided no real value to our predictive models, changing the data types of some columns so that we could use them more easily, and also using labeling coding to split various categorical columns into numerical ones so that our regression models would be better able to use them. After this, we started looking at feature engineering. As you can see from these visualizations, all the zeros, which were caused by filling in the missing NaNs, or the false NaNs, significantly distorted our data. As linear models assume a normal distribution, we couldn't let this slide. In order to correct this, we created a new feature, total SF, which was supposed to represent the total surface area of the entire house, including all of its levels. We calculated this by combining the surface area of the basement, first floor, and second floor. As you can see from these visualizations, this variable was significantly more linear in shape, and we were happy that our linear models would be happy with this as well. After this, we went back to the skewness that we observed for our sales price variable. We knew we had to normalize the data. We tried a few different methods, namely nplog, nplog1, and boxfox1 to try and normalize each variable. In the end, we decided to use a transformation method that yielded the best normalized results for each feature. This meant that every single variable was used in the box-cox method, with the exception of the sales price variable, on which we used nplog to normalize the data. After that, we were happy that the data was sufficiently normalized, and we decided to move on to the modeling phase. We tried multiple different models, and after our 72 submissions to Kaggle, we ended up settling on 4 models: lasso regression, ridge regression, XBoost, and XGBoost. These 4 models, in conjunction, provided us with the best Kaggle score we had gotten so far. We first just simply took the average of these 4 predictions, And then, with further trial and testing, we decided to assign a specific weight to each of these models, depending on how accurate their individual accuracy scores were. After this, we had a pretty decent score, and we decided to use these 4 models in combination with their weighted predictions and average of these weighted predictions for our final submission. My group and I certainly learned a lot over the past few weeks, and we feel like we are ready for any future challenges. Thank you.